recording now. All right. So, yeah, what we're going to do is complete the lecture module 4. And that should bring us to the end of our topics regarding some of the basic calculation work. All right. And what we're going to do, we're going to now consider the notion of, well, let's grow annuities at a constant rate. Okay, so we'll grow annuities. At a constant rate. Of G, that's our basic symbol for growth. So in the previous example, we ran a growing cash flow for 15 years and not forever. Okay, so let's grow this particular cash flow that, let's say, we go back to our equation. The present value is the cash flow in the first period, okay, divided by R minus G, okay, minus that period growing at 1 plus G across time, okay, over R minus G, okay, times 1 over 1 plus R raised to the T, okay. And so for a growing annuity, things look a little different. And we can simplify this a bit. So we could take the present value, okay, of cash flow in the first period over R minus G, okay, times, right, 1 minus, now we're going to go 1 plus G, okay, over 1 plus R. So we're taking whatever growth takes place, right, and discounting the growth by 1 plus R. That's raised to the T. So say at the present value, okay, it's $3. And we're going to divide that by, right, 15%. That's the discount rate, right? Minus 0.06, the growth rate, okay? And that's times 1 minus, so you got to go 1.06 over 1.15. Now we're going 15 years, right? Let's double check your calculation there. This is a tricky one. It's 2352, okay? See, the growing perpetuity ran at 3333, but now we're saying, what if we only grew it for 15 years? It has a much shorter life, so the value is less. So you notice that, right, even though the perpetuity is forever, about 2/3 of the total value came in the first 15 years. This value is in the first 15 years, right? So that's a lesson to look for, okay? Let's see, so 0.6 I want to look at is, let's do growing of perpetuities. Let's grow perpetuities. Or annuities, we can do both of these, right? At, we'll call it a non-constant rate. Okay, so this is, say, an investment opportunity, and it just paid out $3. So you paid $3. Let's say the required rate of return is 11%. Okay, and you expect the growth to run at different rates across time. See, maybe it's going at 15% in years. That's from T1 through T3. Okay. Imagine growth was running, let's say, 10% for 3 years, but these are running T4, right? Through, so that's T4, T5, and T6, right? And then let's say growth is only 5% from time period 7 through time period infinity. So with this one, you'd want to draw a cash flow diagram, right? So that way you could kind of keep things properly in order. So time periods here on our timeline. 8 and thereafter 9. It just keeps going and going and going, right? So, right, it's like we were saying, okay, look, we have a growth rate here, and time periods 1, 2, and 3. So 1, 2, and 3, right? It's 15% growth throughout that span, and we have in time periods 4 and 5 and 6, right? That's when our growth is running 10%. And then, right, going from year time period, right, year 7 and forever, right? So this and this and this, and it just keeps going, right? From here and on, it's running at 5%. Right, so that is not too tough. Once you kind of get that good picture in your mind, you can now, set up your sequence here of present values. Right, you got to run a present value for time periods 1 to 3. It paid $3, right? And grows at 15% across each time period, right? It has an 11% required rate of return. So you got that piece, right? Then you have to add in the present value that comes from, right, time periods 4, 5, and 6. That was running a $3 payout at its base, right? And it grew, right, 15% for 3 periods. And then, right, from for periods 4, 5, and 6, it's running at a 10%. So you got to go, time period 4 is only a 10% growth rate. So that's like saying, well, time period T minus 3, right, helps us to establish our present value analysis, right? So that's discount at 1.11 to the T. And then you have to run, right, a $3 payout. The $3 payout. And let's see, that was growing 15% for 3 years. Then, right, then you had 3 periods, right, growing at 10%. And then you have in year 7, right, it grew at 5% rate. Right, divide by, right, 0.11 minus 0.05. This is the growth rate, remember, of the payout, a 5% growth rate here. Here's a required rate of return, right? So this is R, this is G, right? Minus G, remember? So that times, right, 1 over 1.11, right, to the 6th. All right, so this actually winds up being 7634, okay? Lesson, right? See, this is the amount, this is the maximum you could pay for the investment such that you would get an 11% rate of return, okay? And 11%, right, if you did get an 11% return, the project would have 0 NPV. If you right? If you paid $76.34 for it. If you could get this investment for less than $76.34, your actual return would be higher than 11%, and then you would have a positive net present value. Notice, right, this last part of the example, this piece right here, right? That last part, it's like you're holding a growing annuity instead of a growing perpetuity, and you would just substitute the growing annuity formula for the growing perpetuity formula in the example. Right, so let's do just a couple of examples. Let's call this point 7. And this is just so you can get more practice. And we're almost done here with our topic. Here, a growth rate problem. Let's say it's the end of 1989, and let's say a firm has an earnings per share of $1.50 per share. Let's say it's now the end of 2001, a bit later, and the earnings per share is $6.50. Right? Question we could ask, right? What is the compound annual growth right? What's the compound annual growth rate of the earnings per share in the 12 years of growth? See, now notice it goes 1989. Let's do that, right? It's 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 2000, and 2001. So you see whole years, right, of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You see these 13 years, but how many growth rates are calculated in those 13 years, right? This 1989 amount, right? This amount in 1989, I cannot calculate a growth rate. So the first growth rate calculation has to start in 1990. So I have to have really only 12 years of growth rate. Okay, so this basically works like taking 650, and that's equal to what had been paid earlier, right? $1.50 times 1 plus a growth rate that took place across 12 years. So you just solve for the value of G, okay? And G is 13%. That's the growth rate on average that came about in this situation, right? Let's do a question about doubling your money. How long does it take to double money? Double money value, let's say, right, at 9%. So you got the present value equal to the future value, right, times 1 plus a growth rate raised to t. And you're doubling, so just do, say, a unit where, gotta get my coffee. That's a 1, right? It's the future values. The present value times 1 plus the growth rate across time. Let's double the dollar, let's say. And you're doing it at, let's say, growth rate G here is equal to 9%, right? So multiply by 1.09 raised to the t. And now you just have to solve this for t. So all we did was set up the future value to be twice as large as the present value. I mean, you could use $40 for the future value and $20 for present value. You'll get the same answer. Okay. And the answer here is when you solve for t, you get 8.04 years. Okay. And there's a rule of thumb, a very useful rule of thumb. Okay. The rule of thumb is called the rule of 72. Right, you take 72 and you divide by a whole percentage rate in your problem that I've got here. Got 9% rate, so 9. And under the rule of thumb, it generates for us 8 years. It's a little bit off, right? It's just a rough way of estimating the amount of time to double money. 72 is a constant, okay? So just use that and divide by whatever interest rate you establish. And it's a whole percent, right? You don't put the decimal version of the percentage. So this is the whole percent, okay? So for instance, we said 9%, and that's why you use the value 9. If you had 6.1%, you would say, oh, 6.1, okay? And so on. Now, let's put some of this together into a comprehensive problem, finally. So, let's say you plan to pay tuition for a nephew through 4 years of college. In today's dollars, let's say tuition, that's today, is running $8,000 per year at this particular university that this person wants to go to. And she'll go to the school at beginning of year 8. And she'll if she starts in that year 8, that equals the end, okay, of year 7. So keep that in mind. Tuition is due at the start of the year, and you expect tuition to increase with an inflation rate. Let's say you estimate it to be a 5% inflation rate. You might do kind of a simple forecast and generate such a thing. Let's say the interest rate R is 10%. Okay. So how much do you need to save in years 1 through 7 to help her with this tuition? Let's say you want to get exactly enough money to pay the tuition. Okay, so she's going to start college in year 8 when she makes her first tuition payment, which is, remember, the end of year 7. So the future value and the present value of each tuition payment looks like this. So we could say end of year 7, 8, 9, and 10, because she has to make those payments at the start of years 8, 9, 10, and 11. You can see the future value of the tuition is running 8,000 now times 1.05 to the 7th, right? 8,000 times 1.05 to the 8th. Just do that right down through a spreadsheet. See how we're inflating it, right? So we get, and this is straight off my spreadsheet, 11,257. 11,820, 12,411, and 13,013. Now you just got to find the present value of that tuition using your 10% interest rate. So So you take, right, the 11,257 and discount it back to today, right? So I don't have enough room. You can double check this in your calculator. It comes to, if you're taking the 11,257 and discounting it to year, right, to year one. Okay, so it's 5777. It's 55, 14, 52, 63, and 5024. And you can take the sum, and you see all of that in today's dollars is $21,579. Okay, so you could take $21,579, investing it today, time period 0. Okay, if you're getting 10%, you would have just exactly enough to make the 4 tuition payments, and after the last payment, your account would have a 0 balance. If you save the same amount each year, think about how much you need to save at the end of each year for the next 7 years to get this, necessary amount. Instead of all of it in like one block, save the money each year, right? So you have to take, well, we know we got present value. It's 21,579. And so that's going to be equal to, if you were saving at a constant rate between years 1 and 7, you'd have to solve for C here. And so you remember you're getting a 10% rate of interest, right? So you got to go 1.10 to the T. And C is just the annual end of year savings amount, right, for those 7 years. So that's the annual end of year deposit. C has to be 4,432, and here I won't round, and 45 cents. Okay. So yeah, just some more practice there, and you can try out all sorts of examples as you want in the text, just to give yourself some practice, right? In this course, practicing some problems and checking the answers, and especially I recommend, right, practicing those and then coming to the discussion board and asking other students how they're approaching problems. This is really crucial because I might know how to talk about, the way I approach a problem, but other students, I tend to see do a better job communicating. Peers know their peers a little better than professors these days. So peer-to-peer checkup in a sense. And of course, always come to the professor. And we can look at, the problem that is in Higgins or inside one of the 2 free texts that are in place. Just try to get those problems done. And remember that, right, I want you to be working homework in the Higgins environment. And remember, it's not an accuracy thing, right? It's not for accuracy, okay? I just want it for completion, to see that you're trying it. I'll also be giving you guys, as we started out, the Excel problem. I'll try to give you like 1 per week. And then sometime in the maybe following week, I'll show you the Excel problem as an example. The solved, right, problem comes a few days later. And I don't know, maybe between 5 to 7 days, just so a bunch of people can try the problem, discuss it, and maybe even you could share the the file and try to work on it, and then when you all see the Excel sheet that I'll give you for the answer, what you'll have the sheet, and of course what's going on in the sheet to watch out for is, right, so you have these columns and rows, and so you see a bunch of data, right? So you have the data for the sheet, maybe you were looking at this row right here and you see, oh, okay, so this is a number that was part of the solution, right? And the thing that you want to do is to get yourself hovering over that cell, okay? Because up in the cell's descriptive box, right? So actually you'll have this like real nice descriptor box. And what you'll do, you'll want to find, sitting in that descriptor box, probably is going to be, especially for some of the more advanced stuff, it'll be an equals and it'll be a function of some sort with probably, pointer data. Basically, inside that function, there are values that that the Excel spreadsheet used, and this function is much more important to know than just the answer. The numerical answer is okay, right? But you want to be able to review the sheet and look carefully, right, at the solution by understanding what kind of device that I insert into the sheet, right? And so you have to kind of look at the data, but look at what's kind of hiding underneath it also, okay? And so let's put that at this is the end, right, of lecture module number 4. And we'll put this up on Excel. So looks like we're good to go.